Happy Thursday after a miserable Wednesday. Last time we looked at the dot product. Right, and it always gives us a scalar. Today we look at the cross product, the result of which is always a vector. Specifically, it is a vector that is perpendicular to the two vectors that you're crossing. Right, so cross product always results in a vector orthogonal to both. To calculate the cross product, we set up a 3x3 matrix. First row is the standard unit vector, second row is the first vector, third row is the second vector, and you calculate its determinant. Now, unlike the dot product, the cross product is not commutative, right? That means the order in which you take the cross product does matter. What we're going to do is show that A dotted with A cross C is equal to 0. Well, this is a triple scalar. Do that yet? I'm going to say A is just A1, A2, A3, right? C is C1, C2, C3. So then A dotted with A cross C. You could first find A cross C and then do the dot product, right? Or again, we set up a 3x3 matrix and find its determinant. When dealing with a triple scalar, right, first row is your first vector. Second row is your second vector. Third row is your third vector. If you've taken linear algebra already, you're done. There's a property in linear algebra that says if you take the determinant of a matrix that has two equal rows, it's 0. We're going to assume that we haven't had linear algebra. So we're going to go ahead and take this determinant. The method I'm using is called cofactor expansion, which says I can expand along any row, any column, and then I just have to deal with the minors. For purposes of this course, I'm always going to expand across the first row. So take the first element in the first row, A1. You then cross out that row and that column. You're left with a 2x2 matrix. We multiply by that determinant. 2 by 2 determinant is very easy. That product minus that product. No, that A got erased. Is then minus. Take your second entry in row 1. Then you do the same thing, right? You want to eliminate row 1, column 2 now. And then it's the determinant of the remaining matrix. In this case, it'll be A1C3 minus A3C1. Then plus A3, eliminate row 1, column 3, take the determinant of the resulting 2 by 2 matrix. A1C2 minus A2C1. Just distribute. A1, A2, C3 minus A1, A2, C3. You have a minus A1, A3, C2 plus A1, A3, C2. A2, A3, C1 minus A2, A3, C1. So we get 0. Which now makes sense, right? A cross C, the result is perpendicular to both A and C. So its dot product with A should be 0 because it's perpendicular to A, which we've just shown it is. Yes.
Why is it minus A2 in parentheses, but plus A3 the parentheses? Is it like switch every other?
It has to do with the minor. So it has to do with the sum of the I and J, right? So I represents the row it's in, J represents the column. If that sum is even, it's positive. If that sum is odd, it's negative. In this case, because it was a dot product, right? Right, the dot product of 2 vectors was 0, so it's perpendicular. Going to show that A crossed with B cross C is the same as A dotted with C times B minus A dotted with B times C. I first want to make sure if this actually makes sense. So the cross product of two vectors is itself a vector, right? So we have a vector cross a vector. Okay, that makes sense. So that result will be a vector. If you take the dot product of two vectors, the result's a scalar, right? You can do scalar times a vector. And then if you subtract two vectors, it is a vector. Okay, so at least we have a vector quantity equaling a vector quantity. That's good. If it wound up being a vector quantity equaling a scalar, we'd know something was wrong. So again, just define our three vectors. They're arbitrary three vectors. First, we're going to need to calculate B cross C. First row is your standard unit vectors. Second row is our B. Third row is our C. And take that 3x3 determinant. Just to make life easier, let's go ahead and distribute that negative through. Which means this order is going to switch. Now we can find A cross B cross C. First row, standard units. Second row is A. And I'm probably going to need to give myself more room. I am going to need to give myself more room. And the third row would be the B cross C. Right, so now we just need to take that 3x3 term. This is where the algebra is going to get fun. No. Why am I doing A1? It's A2. B2, C1 minus. And so there's I. The J, A1 B1, C2 minus B2, C1 minus A3 B2, C3 minus B3, C2. So there's our J. And there's our K component. And so distribute. Fun algebra. And so that'll be the resulting I component when you distribute, right? That'll be the resulting J. And there's K. Four. Now we're going to do a little dark voodoo math. I'm going to add in an A1, B1, C1 into the I component. Of course, I'm not allowed to just do that. So I'm going to have to immediately subtract that out as well. So I'm just going to add 0 to it. Right. And the reason for that is if you look B1, there are two B1s, right? One that has A2, B2, one that has A3, B3. Well, I want one that has A1, C1 as well. And it'll be minus. And since I added it in, I have to subtract it out. So there's I. Oh, okay. All right, now for J. We're going to add in an A2, C2, B2, and then subtract out an A2, B2, C2. Why am I writing C's there? They should be B and then C. Minus 2 minus. Okay, now this. There's the J. Then for the K, we're going to add the term A3, B3, C3. And then, of course, immediately subtract it out as well. This is a technique that you're always allowed to do in math. You can always add by 0, and you can always multiply by 1. Right? And you can add by 0 as many times as you want. Right? You can multiply by 1 as many times as you want. The I component. From the first 3 terms, you can factor out a B1. From the second 3 terms, you can factor out a negative C1. J component, first 3 terms, factor out a B2. And then you can factor out a negative C2 from the next three terms. Factor out B3 from the first three terms in K, right? And a negative C3 from the last three terms. Almost there. We can see the light at the end of the tunnel. We just hope it's not an oncoming train. Well, all these groupings are the same, right? It's just B1, B2, B3. So why don't I consider this as one vector? What happened? Oh, that's what happened. That should have been a plus because I distributed the negative through in the J. Right? Yeah, A1, C1 should have been. No, okay, so I have to flip these around. No, but that's still going to leave me with the minus though. Hold on. A1, C1 is here. All right, so that should have been negative. Why do I have it as? Positive here. Uh-oh. Uh-oh. Did I screw something up? Let's see. Right, that's right. That'd be B1, A1, B1, C2 minus. All right, that's right. It's plus. Distribute that negative through. Negative. Means that would have to be plus there as well. Okay, I'm back. That one should have been plus well because I distributed the negative through right after that. Okay, I'm back. The third step after that cross product, that should be plus for the j and then plus for the j in the next step. Because I'd already distributed the negative through. I would make that plus. And this will be plus. Gonna need to move that down. So there's our first vector. There should be a B3, yeah. And then we just do with the C's as a second vector, right? And of course, they're all negative, right? So it'll be minus. Notice that first vector has a scalar multiple. All three components, don't they have A1C1 plus A2C2 plus A3C3? So factor it out. Left with that, right? B1I plus B2J plus B3K. Right, and then same argument, we have an A1B1 plus A2B2 plus A3B3 common in the second vector, so factor out the scalar. That's just B, isn't it? It's the vector B. That's just the vector C. What about this? A1C1 plus A2C2 plus A3C3. Isn't that the definition of A dot C? And what about that term? Well, ignore the minus in front of it, right? Yeah, that term is just the definition of A dot B, right? Which is exactly what we wanted. We're going to show that the magnitude of A cross B squared plus the magnitude of A dot B squared is equal to the magnitude of A squared plus or times the magnitude of B squared. This is a very simple proof. Magnitude of A cross B. How can we write that? And you're trying to do the square root of the sum of the square, right? Sum of the squares of the components. You can do that, but that's more of a headache.
Squared, yes, you could just do A cross B.
But again, that's more of a headache than I'm looking for. You can do that. Magnitude of the cross product is the product of the magnitudes of the vectors times sine of the angle between the vectors. So the dot product is a scalar, right? If you take the magnitude of a scalar, it's the absolute value. But we're squaring it, so we can just ignore the absolute value part. Of course, remember, dot product is the product of the magnitude of the vectors times cosine of the angle between them. Yeah, technically, because it's a magnitude, I should have absolute values in there, but since I'm squaring it, I can just ignore it. Factor out the a squared, b squared. Isn't sine squared plus cosine squared just 1? So you get a squared times b squared. So magnitude of the cross product is, so if you do the magnitude of a cross b, it is the magnitude of a times the magnitude of b times sine of the angle between them. That's a property of cross products. How much in this? Yeah, a dot b is, man, it's just a property. We want to find area of the triangle that has those 3 vertices. First thing. Let's find PQ and PR. PQ would be what? 1, -4, -1. PR. -2, -1, 1. Let's say. Of course, it's tough to do because this is supposed to be in 3 space. Oh, right, okay. So we have those, right? I think of the best way to geometrically represent it, what I'm trying to do. Best way I can think of. That's some unknown vertex, right? But point is, PQ and PR form edges of a parallelogram. The triangle with those vertices is half of the parallelogram, isn't it? So triangle PQR would be half of the parallelogram, PQR, and then, no S. Let's call that missing vertex S. So the area of our triangle would be half the area of the parallelogram, right? I'm just going to label that now as S. That value is the area of our parallelogram. So area of the triangle would be half that area. Right, that means that first we have to find cross product PQ with PR, right? One, -4, -1. I'll write it in component form. So -4 times 1 minus -1 times -1. So -4 minus 1, -5. One times 1 minus -1 times -2. 1 minus 2, -1. But we flip the sign for the middle component. So it's +1. One times -1 minus -4 times -2. -1 minus 8. -9. There's our cross product. Area would then be 1/2 of 25 plus 1 plus 81. So root 107/2. Right?
Can you go over how you ended up getting -5, 1, -9? You said that.
It's the cross product, right? First component would be -4 times 1 minus -1 times -1. All right, J component. 1 times 1 minus -1 times -2, but that's supposed to be minus, right? You flip the sign. So that's why it's +1, not -1. And then K component is just 1 times -1 minus -4 times -2.
Thank you.
And so there's our area, root 107/2, and then we're not given units, right? So we don't have to worry about it. Determine a unit vector perpendicular to the plane containing vectors A and vector A and vector B. Let's just say for the sake of argument, that is our plane. Why did the... Let's say there's A. Say there's B. All right, so both A and B are in our plane. Right, we want to find a vector that's perpendicular to the plane. Well, if it's perpendicular to the plane, it would have to be perpendicular to A, right? It would also have to be perpendicular to B, wouldn't it? And specifically, it would have to be perpendicular to every single vector in the plane. Well, how do we find a vector perpendicular to two vectors? Just the cross product, right? Cross product of two vectors results in a vector perpendicular to both. I'm going to call said vector N. Does it matter if we do A cross B or B cross A? Why? Right. The only thing that's going to change is the direction of the vector. Right, so it'd either be coming out of the plane or into the plane. That's the only difference. So it doesn't matter the order in which you take the cross product. Right, the result is still a perpendicular vector. So without loss of generality, we're just going to do A cross B. And then starting next week, I'm not going to be writing out the matrix. Unless it's like really complicated vectors. -6 times -1 minus -3 times 3. That'll be 6 plus 9. Two times -1 minus -3 times 4. That's what? -2 plus 12. And then flip the sign. Two times 3 minus -6 times 4. That'd be what? 6 plus 24. So there's our cross product. That's not what we were asked for, though. We're asked for a unit vector. Let's make life easy. Factor out of 5. What does that 5 accomplish? So how does that 5 affect the vector 3, -2, 6? Right, so how does that affect a vector? If you multiply a vector by a scalar, specifically a positive scalar. So I saw a hand up over here.
Increase the magnitude in direction.
Right. This 5, all it's doing is it's changing the magnitude, right? It's not affecting the direction. So if we just drop that 5, we still have a perpendicular vector. So here's the vector I'm now going to work with. Just makes now making it unit easier. So vector unit in the direction of n. 1 divided by the magnitude of n. Square root of 9 plus 4 is 13. 13 plus 36 is 49. So there's a unit vector perpendicular to the plane. Is that the only unit vector perpendicular to the plane? How many others are there? Careful. There's only one other unit vector. Right. Yes, there's an infinite number of other vectors, but only one of them will be unit length. What's the other unit vector? Right, just multiply that by -1 and you have your other unit vector. Either one of those answers would have been acceptable. Questions on the cross products? Again, physics people, already saw that. Like this new Teams layout.